USACM Energy and Earth Systems Technical Thrust Area webinar. So, for those who aren't familiar, we sort of cover a variety of different topics that range from climate and Earth system couplings to geomechanics to different types of energy to carbon sequestration, capture storage to oil gas recovery. Please join our TTA if you're a member of USACM because it's free. And also if you'd like to follow, keep up with some of our events like the webinars or any workshops we organize, you can join our LinkedIn page, which is where I advertise a lot of the events. And so we are supposed to have a webinar on May 20th. I don't have a speaker for it yet. I'm still trying to get one. So if that happens, I'll go ahead and send an email. And I'll just say, if you or anyone you know would like to give one of these webinars, either in May or later on in the fall, we're going to take a break for the summer. Please ping me, and we definitely have the slots for that. So before I get to the speaker, I wanted to do this announcement that I've been doing at the past few of these. So we're organizing our first thematic workshop, which is shown here on the screen. The title is Artificial Intelligence and Digital Twins for Earth Systems. So this will be September 22nd through 24th in Austin, Texas. We extended the abstract submission deadline to April 30th. So there's still about a week left to submit abstracts if you're interested. We've gotten already, I would say, more submissions than I was expecting. So I think it'll definitely be a very lively event. So the website, you can, I guess there's no URL here, but if you just type it into Google, this will pop up and you can get information about, dates and plenary speakers and that sort of a thing. So I think you can stop sharing, Valerie, and maybe Hannah can switch to the slides while I'm introducing her. So it's really my pleasure to introduce today's speaker. Today's speaker is Professor Hannah Liu from University of Texas at Austin. She is a tenure track professor there with an appointment from the Department of Aerospace Engineering and Engineering Mechanics. She's also appointed as a core faculty member of the Odin Institute for Computational Engineering and Sciences. Before joining UT Austin, Hannah obtained her PhD from Energy Science and Engineering at Stanford's Doerr School of Sustainability, and then worked as a postdoc at MIT. She has a variety of research interests, which include scientific computing, reduced order modeling, uncertainty quantification, and machine learning in applications of environmental fluid mechanics. And today she'll be telling us about some of her work in scientific machine learning for multiphase flows and porous media. So I'll go ahead, Hannah, go ahead and take it away.
Thank you, Arina, for having me here. So today I'm going to talk about this topic. So here is an outline, and I will start with the motivation background. I am mostly interested in subsurface energy storage. We have a long history of studying subsurface flows, mostly before that was for oil and gas production, because even today, we are still heavily relying on fossil fuel energy. And nowadays, with a variety of energy resources, it is very important to have a steady, sustainable energy system, and we need renewable energy to be combined with energy storage. And the subsurface is naturally a good resources that can use to be like a giant battery and use it to power our energy system. So this Nature Review article summarizes the challenges to be addressed for large-scale energy storage of different purposes. For example, natural gas, CO2, hydrogen, they have very different thermodynamics properties, and natural gas and hydrogen are more active in chemical reactions. And for CO2, we want it to be stored for as long as possible, but for natural gas and hydrogen, we inject it for some time and we want to produce it later. So this subsurface operations is always related to environmental safety problems because injection will increase pore pressure and may bring some geomechanical changes in the fault zones and trigger seismicity. So subsurface is a very complex system. Let's take CO2 storage for an example. Even without active chemical reactions, this process has multi-physics phenomena in like relatively shallow reservoirs. Oil companies use CO2 injection for enhanced oil recovery, and meaning that they also inject the CO2 in the reservoir so they can produce more oil and get more benefits from that. But this part is also as you can see, is complicated multi-phase involves with oil, gas, CO2, and underground water. And in fault zones, we need to consider multi-phase flow also coupled with geomechanical changes to evaluate the risk of induced seismicity. And with different geological formations, there will be like structural trapping, gravity-related trapping, and we see different driven forces. Like near the wells, it will be injection-driven flow, but in much smaller scales, there might be buoyancy-driven flow or viscosity-driven flows. So here is also showing different scales in the system, like the CO2 plume is in local scale, and the pressure changes is far beyond the CO2 plume, and geomechanical changes even far beyond the pressure changing area. And also with the heterogeneity of subsurface, the complexity of the process can be summarized into multi-physics, multi-scale, and full of uncertainty. So we do have physical knowledge about this system over the years from conservation of mass and momentum. We basically have this multi-phase flow equation. And here I'm only considering about two-phase and not coupling with geomechanics just for simplicity. But you can directly observe here the pressure equation is parabolic, so it changes in a larger scale, and the saturation equation is hyperbolic, so it propagates in a smaller scale. So good thing about these equations are they are reliable in providing future predictions with their explanatory power and quantitative error estimates. But it is still very challenging today to simulate physics-based modeling because the expensive computational costs. So for example, this simulation, it is based on the simulation of these equations for CO2 sequestration. It can take days to finish with this resolution. And as you can observe here, some small features, these beautiful dissolution fingers, it requires to be solved at very fine resolution. So the simulation is very expensive for one run. And because of the uncertainties, such as material properties of the porosity, permeability, the location of the fault, initial boundary conditions, and some parameters used in the constitutive laws. For example, the some parameters are hidden in this mobility lambda here, contributing to a large set of the uncertain parameters. So if we present all of the parameters in this parameter P, then it is indeed a parametric system. To assess different scenarios or design an optimization operation, we will need to run the expensive simulation many, many times at different parameter samples to assess the scenarios, and this becomes computationally impossible. So we have the need to find a computationally cheaper surrogate for the parametric systems. And the tools are, the rising data-driven method. I did a lot of studies of this dynamic mode decomposition method during my PhD, which I will show in the next few slides. And many of you probably also know this operator inference. It is developed by Karen Wilcox here at UT. And in the end, I will also show you some cases of using neural networks. I will also share some of my thoughts about how to choose among these three methodologies depending on the specific problems. So generally, we describe a physical system by PDEs or ODEs. We are going to face high-dimensional ODEs eventually after discretization. So as we are illustrating here, it is very expensive to solve the full high-dimensional system, especially for optimization, uncertainty quantification, and control problems, where like thousands of simulations needs to be run. So many research has been done in looking for reduced order models, which are cheap but accurate surrogates of reduced dimension. So a good reduced order model can be obtained in the most informative subspace as efficient as possible, but also preserve the characteristics of the system as much as possible. So it's like you want a simplified instant, but you still want it to be recognized as an instant. A popular data-driven modeling method I studied during my PhD is this dynamic mode decomposition method. This was originally introduced in the fluid dynamics community. In this simulated flow path cylinder example, what DMD first does is it takes all of this collected data from the vortex shading movie, breaking into snapshots or images as they evolve in the time T1, T2, and so on. And then we organize this collected data into two big matrices, U1 and U2. The columns of U1 are my snapshots data reshaped into these very tall column vectors and evolving with time. And U2 is exactly the same, but advanced one more time step into the future. So then DMD does is essentially tries to find a best linear operator A that advances U1 into U2. And remember, these columns of U are of very high dimension, depending on your spatial mesh grid. And so A is a huge matrix. You definitely don't want to really compute this A matrix. So what DMD algorithm actually does is it approximates the leading eigen decomposition of this A matrix, this best fit linear operator A, without ever actually computing A because it is way too big to store to deal with. So I will not go into the details of the computation in the algorithm, but the flavors are singular value decomposition for dimensionality reduction, which gets the dominant patterns from the data, and plus a flavor of Fourier transform in time, which gets how these dominant modes evolve in time. So once you get the leading eigen decomposition of this A matrix, you could use it for diagnostics and understanding the physics, how the flow structure, and what's driving your system of interest. You can also use it for future predictions using this simple model learned from the data and predict how it will evolve in the future. So the key features are the simple model is of reduced dimension because of SVD, and the prediction can be made by computing the eigenvalues to higher power, which can be done in an iteration-free style, making this algorithm a very fast data-driven model. So to deal with the nonlinear system, the Koopman operator theory is saying you can find a transformation map G that lift the state to the observable space, and you will have this observable Y, which has a linear dynamic evolution. And for a linear dynamic evolution, you can easily use DMD to learn. So an example of this kind of transformation is the Kohl-Hopf transformation, which basically you can transform the nonlinear Burgers equation to a linear heat equation. And then by Fourier transform, you can explicitly write out the linear Koopman operator. So now let's go back to the parametric system, and let me show you how we use this DMD method to deal with parametric systems. So let's start with a simple example rather than the complicated multiphase flow. So this is a heat conduction in a complex Stanford logo shape kind of domain. It's because I was doing this at Stanford. So we can take the specific heat C and the boundary conditions SL and SR at the left and right boundary and as the varying parameters here. So after spatial discretization, it becomes a high dimensional ODE system where this capital Phi represents a vector of linear or nonlinear functions. And very often this model output has to be post-processed to compute the quantity of interest by an observation map. For example, this M can be an identity map, which means the quantity of interest is the state variable itself. Or this M can be numerical approximations of the integrals over the domain or a streamline. For example, the spatial distribution of the heat flux. Or for example, the heat loss through the segment of this cavity's surface. So in many applications, this quantity of interest Q are usually much easier to visualize, and they're more comprehensive than the raw output state S. And sometimes the dimension of the Q is much smaller than the dimension of S. So it is more advantageous to solve this high fidelity model for the quantity of interest Q rather than for the state variable S. But here, the function, the vector function f has a complicated form, and potentially we don't know the form of this f. So the question is, suppose we are given several samples in the parameter space and allowed to simulate the quantity of interest Q on these sample points to get several snapshots along the trajectories. Are we able to predict the trajectory of Q at another unsampled parameter point P star at a low computational cost without computing those expensive high fidelity models and going through the post processing? So a general and natural idea would be, to interpolate these snapshots points you have, but the question is how. So kriging is one way. It is non-intrusive in the sense that it needs nothing from the physics or the underlying equations. And this interpolation is done purely based on the distance in the parameter space. And another popular method is projection-based reduced order models. For example, proper orthogonal decomposition, POD. It is intrusive because we needed to know the equation and the observation map. A simple demonstration for this linear case is that we needed to know the full information about the A matrices, the B matrices, and the C matrices at each parameter point. And then we use these snapshots data to identify this reduced order basis V, such that this high dimensional, high fidelity model can be projected into a much smaller dimension R. And the reduced order model is obtained by projecting the operators A, B, and C to this AR, BR, and CR. So after repeating this model reduction procedure at each sampled parameter point, we interpolate the reduced order basis V and AR, BR, CR to get its values at the target parameter point P star. And notice that this interpolation is not trivial and you have to do it on appropriate manifolds. I am omitting the details and you can find it in these very well-known references here, how to do the interpolation. Then essentially we get this reduced order model at this target parameter point P star. And efficient computation can be done at this low dimensional space and be projected back to the high dimensional space afterwards. So POD can be combined with other techniques to deal with nonlinear problems. But the problem will be you have to know this form of the original system and also the observation map. So our way of tackling this problem will still be focused on linear subspace approximation. On this non-intrusive end, we have kriging. We need no knowledge about the physics and equations, but it has very poor performance if the dynamic bifurcation happens because of its like full ignorance of the underlying physics. So unless sufficient data is sampled, this can be less accurate and it may miss some important physical features as reported in the literature. And on this intrusive end, as we just said before, the requirement for the full knowledge about the governing equations are quite restrictive, and one has to deal with the high dimensional state variables. So we want to start with the quantity of interest, and assuming that we don't know or only partially know the form of the high fidelity model. And then we use this Koopman operator theory to construct a linear high dimensional surrogates, and finally using the data to derive the projection-based reduced model. And this procedure can be done in a dynamic mode decomposition algorithm. So we name it as dimension reduction in parameter space, DRIPS in short. So this flowchart can be summarized into 2 steps. During this offline step, the task is to build DMD-based surrogates. At each sampled parameter points, we use DMD to get the low dimensional linear surrogates, and the reduced order basis V and the reduced order linear operator KR needs to be stored. And then during the online step, we interpolate these reduced order bases and parametric ROM at the target parameter point P star. The same way as in POD. Again, this is non-trivial interpolation and needs to be done in the appropriate manifolds. And then once we construct the reduced order model at the target parameter point P star, prediction can be efficiently computed to get the quantity of interest at the target parameter point P star. So let's go back to this previous mentioned example. This left is 2 different solution profiles at 2 different training data points. And the right top is a reference solution at a random sampled test data point. The training data and the reference solutions are obtained from this MATLAB PD toolbox. You know, like with this complicated geometry, the toolbox serves as kind of a gray box because we don't know exactly the values of the discretized operator matrices. Although we know it has kind of tridiagonal matrix form because of the diffusion operator, and then incorporate with the complicated boundary conditions. So we use DMD-based parametric ROM, which does not need explicitly high fidelity model formulations, but you know, like see the bottom here shows the accuracy of the DMD-based PROM, which does not need explicit high fidelity formulations, but very accurate ROM performance with a small rank of 10 compared to the high fidelity model, which requires more than 4,000 dimensions. So we tested the performance of different quantity of interest. The first is the state itself. The second is the spatial distribution of the heat flux. And the last one is heat rate across a segment of the interface. And we choose different observables accordingly and build the parametric realm in 100 randomly draw test data point within this hypercube. So these diamonds shows the accuracy of the realm at the training data points, which basically are on the Cartesian grid. And the arrow increases with the distance from the training data points, as we can see here, because this is coming from the interpolation, and it reaches the minimum at the training data points, where the arrow is only the discrepancy between the high fidelity model and the local reduced order model at the local point. So this table contains the computational cost and accuracy of drips. The averaged, it is averaged over the 100 randomly draw test points. And for these three experiments reported here, drips is more than 4 times faster than the high fidelity model computation, but also maintaining satisfactory accuracy. And the generation of the high fidelity training data during the offline step dominates the total computational cost in drips, and the online speed up becomes more significant when the size of the surrogate model for a given quantity of interest is much smaller than the size of the state variable, because the reduced size of the expensive entry by entry interpolation of reduced order basis. So I'm gonna kind of skip this this part. Basically, we can also use this kind of idea for parametric system to deal with non-autonomous system once we find a way to do a local parameterization for the time-dependent input. So basically, this is saying we can also use this idea to deal with non-autonomous systems. Okay, so speaking of this for DMD for the parametric system, the good thing is it requires low training data requirements compared to more data-intensive nonlinear machine learning methods such as neural networks. But it also has some challenges in highly nonlinear system, especially when the observable map G is very hard to find. I will show you a case where it doesn't work. So in this reaction diffusion system, where we only have one parameter and we change this parameter only a little bit, but because this is a highly nonlinear reaction diffusion system, we can see the dynamics can change a lot. We can see that DMD actually is doing well during the training for the local construction of reduced order model, but it totally went off for just a little bit change of the parameter, so it doesn't work. Basically, it is saying as a linear surrogate model, it is not able to capture this highly nonlinear behavior. But something we also notice here as this reaction diffusion system, it actually has very nice structure. It has like a polynomial structure here. So this is something, you know, we can think of using operator inference because it extends this to quadratic terms as a surrogate model. So this is some current work I'm working with Alexandro Alla from University of Rome and Rudy Glynn from Texas A&M on this topic. So basically, you can think of as this way, with more data, you will be able to use kind of more complicated surrogate models. You can start with linear models, which is basically, you can think of DMD. It requires less data. It gives you a first order linear surrogate model. You can then, with more data, extend this to some polynomial structure surrogate model. You can think of as operator inference in this setting. And if you can afford more data, then you can think of using more nonlinear surrogate models like neural networks. And now I will switch gears to show you an example where we actually use neural networks. Speaking of CO2 sequestration, one of the reasons why we have a delay of large deployment of CO2 sequestration is we don't have the ground truth for CO2 sequestration because the time scale for large-scale sequestration is extremely long. We're talking about decades to centuries here. So we don't really have measurement data for such a long time to validate our physics-based models against. So in this context, the University of Bergen put together what I think is a really fantastic experimental program with a name called Fluid Flower. So they set this meter scale quasi 2D tank with transparent glass panels and put different geological settings constructed by pouring different kinds of sands to mimic the layers of reservoir, the seals as a faults, and the CO2 is injected at designed locations, and the plume migration is visible in this days-long experiment. And they also added some sensors at the back of the tank to collect pressure data. So this experiment is used as a basis for a benchmark study participated by 9 groups around the world. Basically, they get the best subsurface simulators in the world. They want to test if our best simulators can validate a real CO2 sequestration scenario, even just in a lab scale experiment. So here's the result. The yellow contours are the dissolved CO2, and blue contours are the gas CO2 from experiments. And the green ones, the green shades, are the simulation dissolved CO2. And the red ones, the red shades, are the simulation gas CO2. So we can obviously see the big gap between the ground truth experiments with all of our best simulators in the world. And different groups also have different solution provided. And we see that especially for this kind of vertical plume, because of the local faults, this kind of vertical plume is very challenging to capture. And also this small scale dissolution fingers are very hard to capture. So things can be improved immediately after we do model calibration. So this is simulation results from an earlier work of my postdoc group. After manual calibration with experimental data, we can see the simulation model now provides a good representation of the experiments. But the problem is if you ask Louis Salo, who is the main author of this work, about this manual model calibration process, he will tell you how painful it is because there are so many parameters to be fitted and tuned in this system. So some selections can be made with his geological geophysics intuition, but in general, we don't know how sensitive the system responds to each parameter changes. And as we said before, the simulation are very expensive. And we need fine resolution to resolve these small scale dissolution fingers, the vertical plume leaked from the fault. So it's a very expensive process and simulation. To lift the pain in manual model calibration, we want to use machine learning in model calibration. So this is still ongoing work, and today I'm going to only focus on the surrogate modeling part, where we learn a machine learning evolution model from the input samples in the parameter space to different output CO2 migration plume. And what we want to do next is to use this learned machine learning surrogate to do some quantitative sensitivity analysis and then calibrate the model with experimental data to replace the painful manual calibration process. And by doing this inverse problem, the final product will be something like a digital twin for these fluid flower experiments. And the calibrated model will allow us to do some transfer learning to different scenarios of geological formation and different injection plans. So this will be like a very exciting project because it will be kind of a first step to enhance our confidence in trustworthy predictions and real-time assessment for CO2 sequestration, even it's just in a lab scale. So going to how we do this in the input, we have 3 material regions: the storage aquifer, the seal, the falls. And for each of these material region, we have different properties: the permeability, the capillary entry pressure, the concatenated water saturation, the water relative permeability exponent and gas relative permeability exponent, all used in the Brooks-Corey constitutive laws for relative permeability. So 3 times 5, we have 15 input parameters. What is important here is instead of using these 15 input scalars, we borrow the spatial structure, the stratigraphy from the fluid flower tank. So what we actually have here is 5 images given the resolution of our choice. So there are some challenges that we have to face. One is, of course, the 15-dimensional parameter space. It doesn't sound like much, but it cannot be sampled densely. If you want to have 5 parameters values in each dimension, it goes to billions combinations easily. So that's one challenge. The sampling is going to be sparse. And the other challenge is this experiment is conducted in ambient pressure condition, and the buoyancy of CO2 at this condition makes the simulator very challenging to converge for some cases. And this is a plot of the combination of these 15 parameters that leads to the simulations to finish and not finish. So we can see they overlap with each other and all over the space. We cannot really tell in which region this 15-dimensional space will lead to a convergent simulation and which area it will lead to finish the simulation. So we have to take this challenge as it also reflects the fact that the data is always going to be sparser and more limited than we wish. So we just take the finished simulation as our training data set. As we said, the inputs, the 5 images, and the outputs, we use these full field maps for our quantity of interest because it also makes the best use of the spatial correlations. And the input are 6 channels, 5 from the input parameter images, as we said before, and the 6 is represent time, which is a uniform image channel, and the output is the map of the CO2 dissolved in the brine. And we use UNet, a popular convolutional neural network architecture that is tailored for image regression to conduct this learning task. So we have the training data set that are very limited. It's about 80 simulations only, but each has like 466 time snapshots. And here we have the test results for a new combination of the parameters, which is not seen in the training. So these columns are the representative different time snapshots. And the first row is the reference truths from simulation. The middle row are we see predictions from machine learning. And this last row is point-wise error map. I want to point out that this is actually a very challenging task because, as we can see, a big part of these point-wise errors actually attributes to the dissolution fingers from hydrodynamic instability. So the fingers don't necessarily have to be in the same place. So it's actually a very challenging task. And here is another test case where we have similar good match, but just to show you, they have different plume features. And here we have the histogram of the Watson-Stan distance between the test case simulation and the entire training data set of the simulation at different representative times in these blue histogram bars. So basically, this histogram shows the diversity of the data set and the complexity of the distribution, because as we can see, especially at later time, we observe two modes behavior in longer time. And this evolution of kind of a similarity measure reflects that our test case will not be a trivial interpolation from the training data set. And this red vertical line is the Watson-Stan distance between the test case simulation results and the test case machine learning results. So it is a better measure of the accuracy than the point-wise error, because the point-wise error mostly coming from dissolution fingers, but this Watson-Stan distance is a better one for measuring the plume migration. So we can see that this machine learning predict accuracy remains at like less than 1 to -3 magnitude, even when the diversity of the training data set spreads out at later time. So we can imagine that if we do some trivial interpolations like prigging, it will probably do well at the beginning when the data patterns are quite similar to each other, but it will definitely do worse at later time when we have diverse patterns appears. So, but in contrast, our machine learning model is able to maintain this accuracy because of effective learning. So basically, we're summing up the blue bars in the previous slides in the bottom and get the relative accuracy by this definition. Since the top, as we see in the red bar, remains the same order of accuracy over time, and the bottom diversity increases over time. So this relative error is decreasing over time. So this reflects the relative accuracy of our machine learning model is actually enhancing over time. It makes sense, as we know machine learning is a data-driven method, so it will learn better from a more diverse data set with more information from the data. And it shows the fundamental difference between machine learning and conventional interpolation methods. So with that, the conclusion for this part is that our machine learning model is able to learn from a very limited data set and very effectively. And the speed up is significant. And since it is still some early stage ongoing project, we have a lot of ideas to improve the accuracy and robustness of the machine learning surrogate. For example, using more effectively using the temporal correlations, using Watson-Stan matrix instead of the mean square loss in the loss function. Also using a more well-sampled larger data set, and maybe adding physics-informed penalties in the loss function to help with the small data set. we're also working on using graph neural networks instead of using convolutional neural network, because the simulation, as you can see, it actually is constructed in irregular grids because of the layers of different materials region. So it will be more natural to use graph neural network to accommodate these irregular grids. And after we get a cheap and accurate machine learning surrogate, we will ultimately allow us to do sensitivity analysis and model calibration with the experimental data in a Bayesian framework. So which, all of this will not be possible without machine learning surrogates. A future direction of this work will be to enable these bidirectional data flows between this physical twin of fluid flow and the digital twin through the integration of physics-based modeling, machine learning surrogate, and experiments data. So this dynamically updating system requires surrogate modeling for accelerated interactions, which is already shown in this work, and also use uncertainty quantification and data simulations, and also control maybe for the future work. So I'm going to refer to the official definition of digital twins defined in these National Academies of Science, Engineering, and Medicine last year. This is definitely a very interesting topic, also aligned with our workshop happening in September of this year at UT Austin here. So I think I'm right on time, so I will stop here and happy to take any questions you have.
Thanks a lot, Hannah. We're all virtually clapping here. You can imagine. I think I can do I don't know how to do this on the iPad, the clapping, but are there any questions for Hannah? Let me check the chat here. I guess I can start. So in the first part of the talk, I think what you were talking about when you were referencing David Amsalam's group, I was in that group, but we were students at the same time there with Charbel. But I think it was the Grassmannian manifold interpolation. Is that so? I guess like I was just curious because I mean that's an approach where you can essentially, if you have bases for two parameters and you want a basis for a third parameter, you can interpolate them in a way that will preserve things like orthonormality and things like this. But you could also just sort of use just a larger set of basis vectors to build a basis without doing the Grassmannian manifold. I was just curious, like the way that David sold that approach was that it's a lower storage approach. If you're not able to store all your data, it's a good approach. I was just curious if you compared it to just some sort of like a brute force POD on all the data without the interpolation.
Oh, that's a very interesting question. Actually, I thought about this, and actually in this ongoing work, we're trying to compare like what you were saying, like using kind of global basis of everything together compared to using local basis and do the interpolation. We actually find that actually it maybe just of this kind of case, we find that the local basis is performing a little bit better than the global basis.
Okay, that's interesting. Yeah.
We haven't finished kind of a comprehensive study analysis of this, but for some preliminary results we were looking at, I can only speak for this case, we see a little bit better performance in terms of using the local basis interpolation.
Okay.
Yeah. That will also be interesting to do a comprehensive analysis. That's something we are actually consider to do.
Okay. Let's see. Any questions from the audience?
I have a question.
Oh yes, go ahead, Clint.
Hi, Clint.
Hi, Hannah. On the reservoir simulations that you showed, maybe you commented on this, but what was the code that you're using and what's the performance of that code? Is it parallel? Is it?
Yes. So as you can see here, we don't have a lot of stories to tell. So we were using this MATLAB reservoir
Okay.
simulation toolbox, which is, I think, very nice in the sense
Had
that,
Knut,
sorry.
is that Knut Anders Lee's?
Yes,
Yeah,
exactly.
right.
Yeah. So the bottleneck here is because the nonlinearity is solved by the iteration of the Newton method. So you have to set a convergence parameter there. In some combinations of the parameter, the convergence parameter, you have to
Uh-huh.
set it very small, but for the others, you have like different things to set there. If you set just one parameter, some of them will take like much longer to converge. Some will just stuck there forever. So that is part of the reason why we are actually right now in a transition to commercial simulators. It will be faster, more stable, and potentially can resolve many of these failed simulations. Yeah, that is current.
Okay.
Still, I actually love this MATLAB toolbox a lot.
Yeah,
You
yeah.
can open kind of the black box
Right,
there.
right.
Yeah.
Thanks.
Let's see, other questions from the audience? So I guess I'll ask. So the fluid flower, I think they had a demo of that at Science Geosciences in Bergen. Is that right? Or I don't know if you were there.
I was not, but I was
Oh,
talking to them.
uh,
Yeah, I think they're continuously doing very cool experiments and exhibition to
okay.
the museum, to the public, and getting a lot of data too. So it's very cool.
Yeah. I because you're showing. I'd forgotten about it, but I remember seeing it. But I guess I was just curious. Like, so for the surrogate models, how important is it to you that the surrogate be kind of non-intrusive within a code? It sounds like you're moving in that direction with the more of the neural network models, but if you were to do like a Pewdie-Galerkin projection, you have to kind of implement that within your code, and that can take a very long time. And I guess it's related to Clint's question about the codes, but can you talk a little bit about that? Or
Yeah, I think my kind of personal concerns for using intrusive method in this case will be if, like later on, we think about doing more generalization to different injection scenarios, different geological formation scenario, different size of the tank. Intrusive ways will be also taking a lot of efforts there. Also, like if we change the fluids properties, so we actually think non-intrusive method will give us more flexibility in terms of doing the transfer learning setting there. So that is kind of my thinking of that. I do see some literature work of using intrusive methods of building surrogates for multiphase flow problems. But also many other successful stories of using non-intrusive simulations. So that is kind of and since we have the luxury of getting the data in this particular setting, I think we have enough data to do this non-intrusive learning.
okay, maybe if there's one more question or a couple more questions, we have time. Otherwise, we can call it a seminar. Okay, well, yeah, very nice talk, Hannah. We had quite a few people, I think up to 65 at one point. So that's quite a lot. Definitely a lot of interest in your work. So please wait for correspondence from me if we will have a webinar in May or not. And if you would like to give one, or someone who would like to give one in May, please let me know, because I am still trying to secure that speaker. Thank you, everyone. And I may or may not see some of you on the 20th if we do the webinar then.
Thank you, Arina, for having me here.
Thank you.
Bye.
Bye.